talk after class, privately or anything like that with any questions or reservations you have. Okie doke. So we're going to just jump in real quick and talk about our Canvas page for a hot second. Okay, so hopefully you at least found us on on your Canvas page. So this is our homepage. Announcements is the best way I'm going to be able to be in contact with you. Obviously, again, we're an online kind of situation. So if something changes or something weird happens, announcements are a really good way to go about finding out what's going on. If you have the announcements turned off for you, I would encourage you to turn them on. Okay. So I'm going to real quick go down to modules. So everything in our course is kind of organized by modules. The quick links will go up at the end of this week, but basically I wanted you to be able to see everything in the getting started module first, but you'll have a quick link to the Zoom, this OWL dashboard, which will be through your homework and everything like that, and then a quick link to your e-textbook as well. So you'll have that at the top of your Canvas page in terms of organization. Hopefully, if you have not gone through it already, definitely today you are going to want to go through the Getting Started module. I have a little welcome letter here for you. Our syllabus, you'll take a syllabus quiz. You can print out the syllabus, look back at it as much as you want. It's unlimited time. Just make sure you've read it and know what's going on. You've all found the Zoom link. You'll have occasionally discussion boards throughout the semester, just kind of a place for either like a practice question for everyone to kind of, feel it out for themselves, talk to each other about it, that kind of thing. So the one for this week was on expectations for this class as an online class. And then we get into the homework. If you have, or like our textbook / homework, if you have not done so already, I would encourage you to go through and read through the Read Me First document. I'll kind of explain what's going on. If you are waiting for financial aid, that's totally fine. It won't be a problem. Danielle, yes.
Hi, I was just wondering, I registered for the like the Senage thing, whatever it's called, and it was asking me for an access code and stuff for the ebook in order to, or no, an access code in order to enroll in the class through there, and I wasn't sure where to find that.
Sure. So our class had to start first.
Oh, okay.
So like it didn't exist until today. So again, that's why we don't like pressure too much on like being able to get started right away. So what I would encourage you to do is go through this document here. It will kind of give you the instructions, but basically all everyone has to do to get started with getting your textbook and the homework, click on the Getting Started with OWL assignment. It will automatically load everything up. It will send it straight through your Canvas. It will log everything, take all of your Canvas and everything with it. So if you click on Getting Started with OWL, this assignment right here, it will kind of load everything up and kind of guide you through the process. I would encourage you to do the Read Me First document just so you know what's coming and that kind of thing. But to get started with the class, you bought an access code through the bookstore or whatever, no problem. Otherwise, you'll have a free week. Basically, what will happen is if you are waiting on financial aid or something like that for purchasing your book code or whatever we want to call it, you can get started right away. Click the Getting Started link and you'll make your account, all that kind of stuff, and you get a free week. So you'll be able to get started and wait. If you're still waiting at the end of the week of the 7-day trial, and you still are waiting and being held up on your financial aid, please let me know. We have a very good rep for our book, and I'll be able to get you a little kind of extension if necessary for that. So just let me know if that's an issue for you, and we can take care of that. So OWL is our homework, which is still through the publisher, the Cengage. So OWL is just what they call it, but it's all the same thing. And then your textbook is through there as well. It's an e-textbook. If you are someone who likes to write and write all over your textbook and whatever, go find the older version on Amazon. of the textbook and just buy it and have it for your own copy with that. What's nice with integrating the homework with it is for the homework sets, you can actually, when you're stuck on a problem, you'll have the link to the section of the textbook and that will jump you right to it. So if you've never used it before, it is pretty handy in terms of being able to determine materials and help with that kind of thing. We will need to scan some things. So for tests, primarily, we'll do one quiz where we kind of proctor it on Zoom just to kind of get everybody used to it before the exam. But you will need to show me your work for your exam. So if you do not have a scanner at home, I have some nice apps in this document here that are useful. What's good is this is probably not your first round of online learning, so everyone's kind of figured out how all this works. All right, week 1, we're going to jump into it right away. In about 2 minutes, I'm going to get started on lecture. So basically the way the modules are set up is kind of what will happen per day with assignments, lectures, everything like that. I strongly, strongly, strongly encourage you, do not just look at your dashboard and go, oh, this is due today. If you do that, you're probably going to miss really important information. You actually have to go to the dashboard because not everything is due. Some of it's just files that you need to read to do the assignment. So this class is a lecture and a lab. So today we'll do chapters 1 through 3. I really, really encourage everyone. Obviously, we only have so much time and we have a lot to cover. So there will be a lot of times where you'll need to kind of find some stuff out on your own. And I've well manicured and curated some very good videos that will help with a lot of things. So those video resources, the non-graded ones, are really, really helpful as well. It is encouraged and expected that you are going to read your textbook, and then the beginning of each lecture, I will open up to questions and we'll go through the questions on things that you've read or any questions you have before we start the next lecture. Again, kind of going with that whole accelerated class thing. We only have 2 days to meet. Usually in the summer, this course meets 4 days a week, but with the online situation, this is all we were given. So it's going to be a lot on you guys. I'm here as a resource, but it's going to be one of those things where you're driving the boat and I'm here to help. You do not need to buy anything for lab. It will all be provided to you via our, modules and everything like that. So as you can see here, basically these README files will be PDFs from our manual, basically, that I've uploaded for you. So for lab, you're going to read the safety thing. Basically, we're just trying to get you prepped if you ever go on to do an online or a non-online lab. What you would need to know, some safety videos, and there's a safety quiz. And then your first experiment is an experiment on scientific notation and significant figures. And then real quick, just to let everyone know, day 2 this Thursday will be no Zooming because I will be traveling. And when my travel was originally planned, my flight was on Wednesday and it wasn't a problem, but now it's on Thursday. Unfortunately, I need to get out to the East Coast to see some family for some important things. So I will still be Zooming from the East Coast. It won't be an issue. It's just that day. These will be pre-recorded lectures, just like if I was talking to you. So if anything, it'll be something that you'll be able to pause and slow down and that kind of thing. There still are extra help videos for that, but those pre-recorded lectures will be graded. So Canvas does allow us to see if we make an assignment video, we can see if you've watched them. We can see if you've skipped through them. So these are videos that you will get a grade for, these 3 right here. All right, and then here are the homework assignments for this week. These are in addition to the getting started homework assignments that are in the getting started module. And then down here, there will always be unit resources. So these will be things like worksheets, all sorts of stuff. I give lots and lots and lots of resources for you guys, lots and lots. And then the keys are always, pretty beefy. So if you're having, an issue with something and you want more practice with it, I make the keys pretty beefy in terms of their explanations. One thing though, students have a tendency to do is be like, I'm just going to look at the key. And they go, yep, I know that. I know that. I know that. I know that. you don't know it. So go back and do it and then look at the key. When you look at the key first, of course, you know it. So just don't put yourself at a disadvantage. But like I said, my keys are pretty beefy. So you should be able to, if you have a question, obviously, I'm more than happy to help and go through it. But I give a lot of resources in this class because it's a lot. It's a lot. The GOB is a challenge when we're not 8 weeks in online. And then lastly, for today in chapter 1, there is a lot of math. But the problem is we need to cut some time out. So what I've done is I've gone through and put the dimensional analysis guided practice with it's basically an additional PowerPoint that is here for you that goes through how to do all the math and everything. So lots of practice problems in here as well. It's just we don't have the ability to go through and do a whole bunch of practice problems during lecture. But again, please email me. My office hours are going to be after lecture, but if those don't work for you, we can meet outside of that. Just email me and we'll set up a time that works for everybody to do that. All right, so I'm gonna go like this for a sec. Any questions before we begin? All right, everyone's just blown away and going, holy hell, what did I get myself into? Yeah, all right, so we're gonna jump into it. So these are lecture slides that are posted onto the chapter 1, 2, 3 section of week 1. So like I said, this is fine. 8 weeks, 25 chapters. Let's do this. All right. So I will always kind of put this kind of stuff up here just so you can kind of know what's going on. So here's our unit 1, the first 3 weeks of class, unit 1. We'll have a quiz that's due by the 24th, or excuse me, 26th, which is Friday. So that's your first quiz already. It will be done on the same platform that your homework is done. Our quizzes and tests will be done through that platform, which will hopefully help you get a little more familiar with it as you're doing your homeworks. It won't be like some other thing that you have to learn. Chapter 3 quiz, we are going to do via Zoom in class just to give you practice on like a low stakes thing before the exam, because the exams will be done via Zoom and that whole thing. So it's just kind of a practice so that you know how to do it all and get set up with it and everybody kind of gets it. That way, when we have the exam, you're not like all stressed about it. All right, so chemistry is the study of matter. I would encourage you guys moving forward, if you can, print out these lecture slides just so that you can start writing on them. If not, you're going to want to either have a notebook or something to write in just so that we can get through it. So matter is basically everything that we, exists. But when you think about it for a second, things that aren't matter that we deal with on a day-to-day basis would be something like light or energy. These things do not have mass. So matter is something that has mass and occupies space. Something like light or energy, which is a form of, or light is a form of energy. These aren't considered matter. So typically we will be dealing with things like molecules and atoms. We will be dealing, when we get to our biochemistry section, with things called macromolecules, which are just really big molecules. But we're going to start from teeny tiny atoms and work our way up to molecules. The molecules are the smallest particle of a substance, right? So if we're talking about a water molecule, one individual molecule of H2O. And in that H2O, hopefully everyone kind of is familiar with the concept of water being H2O, it has 3 atoms. Atoms are going to be the smallest identifiable unit of an element, okay? When we get smaller than an atom, which we can, we know there are protons, neutrons, and electrons, and we'll go through that. We can't say, that is a hydrogen electron, and that's the proton from an oxygen. We can't do that. We can't identify them like that. We can go, that's an oxygen atom though. So an atom is the smallest identifiable unit of an atom, or excuse me, of an element. So the first thing we need to do is be able to kind of classify things. Chemistry is all about classification. We do it with how we name things. We do it with how we call out, different kind of subgroups and everything like that. So what we want to do is talk about how we can kind of call out different groups of atoms. So a lot of times what we'll see are these kind of like prefixes or suffixes, which would be at the end of a word, that help kind of classify things. So if we have a diatomic molecule, that would be something that contains 2 atoms. Triatomic would be 3. Poly is anything more than 3. And then we also have the prefixes of homo and hetero. If you're not familiar with this, homo would be things that have the same kind of atom. So if we have a homoatomic molecule, that would be maybe a diamond. A diamond is made, a pure diamond. A diamond is made solely of carbon. That would be a homoatomic molecule. A heteroatomic molecule will be something that has different kinds of atoms. So back to our example of water, H2O. This would be an example of a heteroatomic. So homoatomic for same, heteroatomic for different kinds. When we're going through classifying matter, right, we're going to keep growing on this concept. We're going to have elements. Elements are pure substances of homoatomic molecules. So homo being same, right? So individual atoms of it. I could have a sample of copper. I could have a sample of oxygen. Sorry, that's my kid screaming in the background. We can also have things called compounds. So a compound is going to be a mixture of different elements. So a compound will be a heteroatomic molecule because it's going to have different atoms in it. Water, sodium chloride, which is table salt. We are going to find throughout our time together that words that you hear in your day-to-day life have a very different meaning in chemistry than they necessarily did in your day-to-day life. So salt, as we say it in day-to-day life, refers to the stuff you put on French fries. Salt in chemistry, there's my kid freaking out. Salt in chemistry refers to typically a non-metal metal combination ionic compound. So we're gonna, there will be some differences there. So you'll always hear me call out when I'm talking about sodium chloride, I'll say table salt to classify it. So here's just a really nice kind of flow chart to help with kind of what are these classifications that we're talking about, right? General idea of matter. Matter is things that have mass to them and occupy space. And we can have 2 different kinds of matter. We can have pure substances or we can have mixtures. Under pure substances, we have elementally pure things like just a hunk of copper, a hunk of hunk of graphite for carbon or whatever like that. But we can also have pure substances like a compound, a pure compound. What if I had just a glass of pure water, only H2O molecules in there? Yes, each of those molecules is hetero, different atoms in there. But when I look at that sample, the only things I find in there are water molecules. I would have a pure compound. On the opposite side, we would have mixtures. We can have homogeneous mixtures and heterogeneous mixtures. The easiest way to kind of describe this is a homogeneous mixture or compound or anything like that is going to be something where I can't say, yes, there is the copper, there is the zinc. So something like brass, alloys of metals. For example, I'm going to date myself now. Rose gold used to be really, really, really popular. Rose gold is, there's no gold that is pink color. What they're using is an alloy of gold and copper, and they're mixing those together, and the copper helps kind of give it a pinkish color. But you can't sit there and look at a rose gold ring and go, there's the gold, there's the copper, there's the gold, there's the copper. So this would be homogeneous. It's completely mixed to the point where we can't distinguish the pieces in it. A heterogeneous mixture, the best way to kind of describe it is anything where I could pick apart the pieces. So even though you might not necessarily think of this as a mixture, right? If I just had a bunch of pennies sitting in a glass of water, if I'm looking at that sample, it's water and copper, but they're not mixed well together. I could literally pick out the pennies. So that would be a heterogeneous mixture, something where I can distinguish the pieces apart. Another example would be like a chocolate chip cookie. That would be a heterogeneous mixture, right? I could pick out the chocolate chips from the rest of the cookie. But like a sugar cookie where I can't say, yes, there's the flour, there's the egg, there's the sugar, that would be homogeneous. Okay, I'm going to take a very hot, quick detour to chapter 6 because I don't like how our book outlines this in terms of, when introducing matter kind of thing. But you won't get tested on it. You'll get tested on it in chapter 6, but it just makes sense to talk about it now. So states of matter. The classic example that we always use for this will be when we're talking about water, because we've all seen water as a solid, which would be ice. We've all seen water as a liquid, and we've all seen water as a gas, right? A cloud, steam, things like that. So water is always a really good example. I always try and use examples that you all have seen in your day-to-day lives so that you kind of have something to go on in your head. So when we're talking about solids, rigid, fixed shape, fixed volume, right? These are things that, you know, if it's a solid, it has a specific shape, it has a specific volume, all that kind of stuff. A liquid, while it does have a fixed volume, it doesn't have a fixed shape and it's not rigid, right? Think about it. The shape of water is going to take on whatever shape the container is. So I could have a very ornate vase and that would be the shape of my water sample, or I could just put it in a bowl and that would be the shape of my water sample. And then lastly, a gas. Gases are not rigid. They have no fixed shape, right? Again, similar to water in the terms of they take on the shape of their container, and they have no fixed volume. Gases can be compressed or expanded. So, right, think about a balloon. I can squish a balloon. Yes, there comes a point at which it pops, but I didn't take any gas out to squish that balloon. So it doesn't have a rigid volume. Again, we will go into more detail with this in chapter 6. So I'm going to kind of breeze through the solid, liquid, gas thing, but just kind of giving you an idea of these states of matter that we're going to be talking about this semester. When we talk about rigidity, what we're talking about is the arrangement of the atoms. So a solid has a very set arrangement of how the atoms line up in that sample. A liquid, they interact with each other, but just like a liquid flows, they kind of mush on top of each other. And then a gas is very similar to like small children in a bounce house. They're just kind of bonking into each other and then flying off the walls and that kind of thing. They are kind of doing their own thing. The last thing, one of the last things we're going to talk about in terms of not math things in chapter 1 is the difference between chemical and physical properties and chemical and physical states. So a chemical property and a physical property, these are kind of distinctions in telling us things about the matter that we're looking at. A physical property is something that we can observe or measure without changing the substance in any way. So color or size or, hardness. A chemical property demonstrates its ability to do something when it changes. So paper can burn. That's a chemical property, right? When we burn it, we're changing the composition of the paper, but it's a chemical property of it. So down here, I have just some examples that you can go through, right? A match burning would be a chemical property. Melting. Let's go back to water for a second. If I have an ice cube and it melts, did that change the chemical property of the water? No, it's still water, right? Just because it was ice and then it melted, it's now liquid water. It's still water though. It's still H2O. So melting, boiling, freezing, these are all physical properties. Those are the ones a lot of people get kind of hung up on. If I crush a rock of limestone, this would be another physical property. It's now just limestone dust. It's not a rock, but it's still limestone. If the limestone is heated and it decomposes and it produces lime and carbon dioxide, now I've changed the chemical properties of it, and now it's a chemical property. So these are just things that we need to kind of think about as we go through it. For here, the chemical and physical properties of copper I have. So these would all be physical properties, and then chemical properties would be things like, its ability to, react and oxidize and things like that. So we have chemical and physical properties. We also have chemical and physical changes. So we talked about already, right? This idea of melting, freezing, boiling. We could also talk about condensation, those kind of things, right? All the things water does. These are physical changes. It's changing its physical state, but it's still water, right? When I go from ice cube to a glass of liquid to steam, it's still water. It's still H2O. In no way have we changed the chemical the chemical composition of the material. And because of that, we are not having any chemical change occur. It's just a physical change. And so sometimes it's really hard for students to kind of grasp. So when you're looking at an example and it's asking you whether it's a chemical or physical change, always go to water and go, if the water melted, it would still be water. So that would be a physical change. A chemical change would result in a new substance or something with different properties. So for example, here I have a picture of iron rusting. Iron, just like an iron nail that you get at Home Depot, is just iron. It's an elementally pure compound, right? It's a substance that's pure. It's just iron. But as it begins to rust, the rust on the outside is actually this compound right here, iron 3 oxide. So it's actually a new compound. So this would be a chemical change. So something rusting is a chemical change. Here I just have some examples for you, kind of summarizing what we just talked about. Welcome to science, and in science we use the metric system. I know America is probably the last place, that's still like, hey, let's not be on the metric system, but that's cool. It got us to space and it got us to the moon, so I guess we shouldn't complain. But in this class we will predominantly be using the metric system. So things like meters, centimeters, that kind of thing. We will be using milliliters, grams, Celsius. We will occasionally, when we get to gases, use Kelvin, and we'll talk about why we need to use Kelvin when we get to it. But that has more to do with math than anything else. In Kelvin, there are no negative temperatures. And for some of the calculations we do, it would be really weird to have like solve for a volume. And if there was a negative in it, the math would then make it like a negative volume, and that wouldn't make any sense. So that's why we use Kelvin. Your homework will go through plenty of practice with you in terms of kind of getting familiar with the metric system if you aren't already. Here, obviously, at this point, you're probably familiar with the concept of length and volume and mass and that kind of thing. So typically we will use meters. When we're talking about very small things, it will be centimeters, nanometers, and these are just kind of smaller increments of a meter. In volume, we will typically be using liters, milliliters, that kind of thing. In a health setting, you typically use a cubic meter. So a cubic meter basically is going to be meters cubed, right? So a cubic meter would be length times width times height, which would be a volume, right? So that's where we're getting it. But what's nice is 1 cubic meter is the same as 1 milliliter. So it works out. It's a pretty easy conversion. Again, you can go through and look at these on your own, but if we're measuring height of someone, we would want to be in meters. If we're looking at a race, we're typically going to be using seconds in our class, kilograms, and then Celsius or Kelvin, depending on the environment that we're talking about. Okay. Another thing that is really, really important, your lab will go through a lot of practice with this, and you'll have the opportunity to read a little bit more on it as well, is the concept of scientific notation. Chemistry is notorious for having really, really big numbers and really, really small numbers. So when you're using your calculator, probably up to now, you've probably done something where you're like, okay, I'm going to write out the width of a human hair, and I'm going to sit there with my calculator, right? My calculator, I'm going to go, okay, 1, 2, 3, 4, 5 zeros. And you're going to count 1, 2, 3. Okay. That's a really good way to screw things up, right? Think about it. When you're on a test or a quiz or something like that, or doing your homework, and you're sitting there counting, oh, 1, 2, 3, right? How many times are you going to screw up how many zeros you put in? And then your number's wrong because you screwed up the zeros. So we're going to work towards using scientific notation. And that gets rid of those zeros before and that whole thing. And it'll be a really nice way to represent really, really big numbers where you have a lot of zeros after, right? If you're writing out 5 million or 10 billion or something like that, or if we have a really, really tiny number, right? So number of hairs on your head, right? We have, you know, a bunch of zeros here. We can write it out like this. So scientific notation, we can kind of think of it like grammar, like for writing numbers. We're always going to have all our significant digits, which I'll talk about in a second, beforehand, times 10 to the something. That's the grammar of it. That's scientific notation. It's always going to be numbers here. We're never going to have zeros here. Okay. Times 10 to the something. That's the grammar of scientific notation. We will be using power of 10. That's the base that scientific notation is put in. But here you can just see some examples if you struggle with kind of visualizing what a positive exponent versus a negative exponent would be telling us. So for example, if I had to go out 1, 2, 3, 4 decimal places, I could write this number just like this: 1 times 10 to the negative 4. So when the decimal place has to go this way, it's to the negative. If I'm going 4 decimal places this way, 1, 2, 3, 4, then it'd be positive 4. Okay. Like I said, you'll have a lot of opportunity for practice with that in your lab, as well as in the resources at the end of the unit. That guided chapter 1 practice has a lot of examples with that. So here is just kind of a reiteration of this when we're dealing with converting scientific notation. So when you have a number that basically how you've always written numbers, we call that standard notation, right? We're just like 2.457. That's standard notation. Scientific notation would always be to write it where we use that proper grammar. So, sorry, I'm outside today, so there's construction going on. I live in Poway, so there's like horses and goats and everything, and my neighbor's pig has arthritis, so at some point you'll probably hear some terrifying noise. It's just a pig. When we have scientific notation, we're always going to be in powers of 10. And what we want to do is always move the decimal place. So we have integer, decimal place, and then if there's any other numbers that we need to write, it comes after it. So it's always going to be like 2.457 or 1.782. We're never going to write it as 24.57. It's always going to be just one integer, then the decimal place, and then any of the other numbers that we have to add after it. Again, when we have positive versus negative exponents on the 10, it's just which direction the decimal place has to move to get it to that proper grammar. If we have to go to the right with the decimal place, it's going to be a negative number. If we have to go to the left with the decimal place, it's going to be a positive exponent. So one of the really important things that we need to talk about, and this comes up in scientific notation, is how we represent measured numbers. And this is really important because up until now, you've probably taken for granted when you measure something with a ruler, or if you're looking at, a patient's weight on a scale or something like that, whatever number comes up, you take that as, well, that's the number. But what we have to understand is the instruments that we use to measure things with are inherently flawed. And there's a level of precision that comes with different instrumentation. For example, this ruler here, right, centimeters, and then we go down into tenths of centimeters here. But what if this ruler only went 0, 1, 2, 3, 4, 5? I wouldn't be able to as accurately give a measurement with a ruler that just went 1, 2, 3, 4, 5 than I can with a ruler that has more markations on it. So the instruments that we use to measure with are important because there are inherent accuracies and precisions that come with those. And when we record a number with them, we can't just go out willy-nilly with our decimal places. So oftentimes you may have had a math class where they're like, that's cool, just go out 2 decimal places and that's what you record. Moving forward in this class, we can't do that because what we could potentially be doing is adding more certainty to the number than is actually there, or we could be taking away from the certainty of the number. So we need to talk about this concept of what a significant figure is. A significant figure is basically a way for us to know, when I look at a measured number, how certain is the data? How far out can I go? So whenever we look at a number on a piece of paper that's recorded and we see a non-zero number, that number is significant. We have to keep it. If I have zeros between non-zeros, those numbers are significant. So all of these numbers here are significant. So SF, as you see it here, is just standing for a significant figure. Zeros at the end of a decimal. So this is where we start getting this precision thing that I started talking about up here. 50.00 meters. What this tells me, these zeros here, tells me about the instrument that was used to measure the number. What this means is I know, looking at this recorded number, that the precision of this measurement goes out to the hundredths place. That's what it's telling me. If I used a different instrument, it may have only gone to the 10th place, or it may have gone to the thousandths place. It depends on the instrumentation being used. When we write a number in scientific notation, whatever comes before the 10 to the, if you see a number written like this, however many digits are here, these are all significant. So the tricky part for you will be is if you see a number in standard notation and you have to write it in scientific notation, you're going to have to figure out which zeros I keep and which ones go away, which ones aren't significant. So for example, I have two measurements here, 5,000 kilograms with a decimal place. That decimal place is saying, this is where my measurement ends. I can only go to the ones place with it. That means that all four of these numbers, these three zeros are significant. So when I write it in scientific notation, I have to write it like this. However, if a number was recorded as 5,000 kilograms, when I write it in scientific notation, these zeros come after, there's no decimal place after them. So these zeros are not significant. I understand that they're placeholders, and that's what this 10 to the 3 is doing. It's representing that placeholder of a magnitude, but they're not measured with significance like the decimal places here. So remember what we talked about at the beginning, this concept of things that we do in day-to-day life versus things in chemistry that are different. Putting decimal places and writing something like 5,000 is different in chemistry. It has different meaning. We do have things called exact numbers. And one of the things is sometimes students get a little confused with this. The way I like to explain it, and this will make more sense when we do math, the way I like to explain it is exact numbers are counting numbers. So like whole things, like I have one calculator. It's not like I can have 1.5 calculators, or I have 2 children. I don't have 2.5 kids. I have 2 kids. I don't have like a set of legs running around in my house right now too. There are whole numbers where you can't have a decimal place of it. You know, there are 60 minutes in 1 hour. It's not sometimes going to be 60.2 minutes and sometimes 58.9 minutes. It's always 60 minutes. And when we have these exact numbers, we say they have infinite number of significant figures. It basically would be like writing, if I was saying 60 minutes in 1 hour, I'd be writing it as 60 decimal place 0.0000 for infinity. It's an exact number. It will always be that same measurement. This will be important when we start talking about using these in math and doing math problems. So when we start doing math with measured numbers, where we have to talk about the significance of the numbers, we need to be careful how we round. Again, you may have had a math class where when you round something, you may have had an instructor who just told you, just go 2 decimal places and that's good. We can't do that in chemistry because we may, like I said, we may be adding or taking away from the accuracy and the precision of the measurements that we use. So we have rules that go along with it. So for example, if I wanted to take this number here and round it to 3 significant figures, we're going to come out 1, 2, 3 significant figures. I look over one more. We're going to go with the rule of 4 and less. We drop it, and if it's 5 or greater, we're going to round up. Okay. there are all sorts of different rules people have with this, and we're not going to get into the debate, which is the better or worse. This is how your textbook is doing it. It's a perfectly fine one to go with. So we're going to round if it's, we're going to round down if it's the number 4 or less for the number afterwards. We're going to round up if it's 5 or more. Okay, so when we have significant figures and we're doing multiplication and division, so let's say I'm taking these two numbers, right? Let's say these were lengths that I measured, and for some reason I need to multiply them. Basically, when I do multiplication with significant figures, I can only report my answer with as many significant figures as my least significant measurement that went in. And the reason we do that is our answer cannot be more precise and more accurate than our, the data that went in. We can't make up data. So in this case, we had 4 significant figures in this measurement, and we only had 2 here. Remember, these 2 zeros come before the non-zero numbers. So we could rewrite this in scientific notation, and these zeros would go away. So I have 2 significant figures here and 4 here. So when I multiply this in my calculator, I get this number here, but I can only report 2 significant figures. So I could come out 1, 2, I look over, this is a 0, so it's going to round down. So my answer would be 5.3. So multiplication and division use this same kind of logic. Addition and subtraction, we use different logic. So I will leave this up here for you. Again, like I said, there's a lot of practice with this at the end of the guided practice in the resources section. Let's talk about addition and subtraction. When we do addition and subtraction, we're looking at number of decimal places, not total number of significant figures. So here is an example with addition. So this number has 1 decimal place. We go to the 10th place. This number goes to the 100th place. When I add these up, right, this is what my calculator would tell me. However, I can only go to the 10th place. I can only report this number to the 10th place. Questions with that? I know I'm trying to fly through it so that, we can get through our material and you can at least hear me talk about some of it. Okay, we're going to move on to prefixes. So you may have seen these kinds of things before, right? We already talked about with di, tri, poly, that kind of thing. But when we're talking prefixes in math, what we're talking about is you've probably heard of a milliliter, a centiliter, a milligram, a centigram, that kind of thing, right? So these are prefixes, and they kind of just tell us what decimal place we're measuring at. So if we go back and we look at our ruler for a second here, right? Oops, come here. Centimeters, right? Centimeters on a ruler, like, one that you keep in your desk, is pretty common. But basically the base unit there is a meter. And it's telling us that there are, demarcations that there are 100 centimeters in 1 meter. And then a millimeter would be 1,000, which are these little guys here, 1,000 of these in 1 meter. So when we look at our prefixes on this chart, like we're talking about here, 10 to the 3, right? Or 10 to the 2 for centi. The ones we will typically be using will be centi, milli. We'll use a little bit of nano. Those are the smaller ones. And then the bigger ones would be things like kilo, mega, giga. Typically, we will see centi, milli. We'll see a little bit of micro, but we'll see some nano, and we'll see kilo. Those are the ones that we will see the most of in terms of prefixes. Your homework will give you the whole range of them. Real quick note on the homeworks. Homework will be harder than the tests. Homework is the opportunity for you to kind of explore the harder stuff. Homeworks, you have unlimited tries, all right? Like literally you've got a week to do it. You can submit till you get it right. So you could get 100% on every single homework. It's completely possible. I encourage you, after the 3rd or 4th try, email me. Don't just keep banging your head at the wall because you're going to throw your computer out the window, okay? Like email me and be like, what am I missing here? I can see what you're submitting and I can see your work. So I might be able to go, oh, you're off by a factor of 10. What would that mean? Or, you know, oh, you forgot that oxygen is O2 instead of O, and that's why you're off by 2, and, you know, that kind of thing. So, you know, simple things where it's like, you know, what's going on, but like you forgot something. Or, you know, when we get to the organic chemistry, there's challenges with learning how the drawing software works. And that can be really frustrating for students. So just email me, reach out to me through the Canvas Pronto or whatever, and I'll help you out. There's no penalty for, you know, trying it 10, 12 times, you know, to get the right answer. That's fine for the homework. That's why they're harder problems on the homework, okay? Equalities are something we're going to see a lot of in chemistry. It really helps us do a lot of problem solving. You've seen plenty of equalities. I've already used one in our lecture so far today. I said there are 60 minutes in 1 hour. 60 minutes equals 1 hour, right? Basically, this means I could say 60 minutes, or I could say 1 hour, and it would be representing the same measurement. The same way I could say 1 kilogram or 1,000 grams. Okay, these are equalities. And we will use them a lot, especially when we get to kind of concepts of things like how many grams of this equals how many molecules of this, or how many grams of this is how many atoms of this. Okay, so we will use equalities to figure that out. From a medical standpoint, one thing you've probably heard about before, if you work in a medical field already, you've probably heard, you know, when you're administering a liquid therapeutic to a patient, it's measured in cc's. Cc's stand for cubic centimeters. It's a measurement of volume. Centimeter, right? When we said before, right, that volume could be this meter cubed. Well, meter cubed would be a whole lot of something you're giving a patient. Centimeter cubed is a much more reasonable, probably, volume that we would be administering to a patient. So in the medical field, we use centimeters cubed as our volume measurement. Instead of milliliters. But 1 centimeter cubed is the equivalent to 1 milliliter. So if you're told, you know, you have to administer 350 cc's to a patient, you're giving them 350 mils of whatever therapeutic needs to be administered. So oftentimes what we'll see end up happening is different fields have different kind of pet preferences of which unit of volume or measurement that they prefer. So again, when we're talking about these equalities, we could write them as fractions. And this is a little more on the math heavy side of things. We could write them as fractions, right? 60 minutes over 1 hour is equivalent to 1 hour over 60 minutes. These can be written both ways. And what this allows us to do is to go ahead and start utilizing these in math problems. So we'll start seeing that. For example, this is very, very important and useful if you are, you know, in a situation where you need to give us, you know, a patient a dosage of something, and you just know, okay, it's 50 mgs per every kilogram that the patient is, and you've got to go look at their chart and figure out, okay, well, they weigh, you know, 75 kilograms. You know, you got to go through and figure out, well, how many milligrams do I need to give them, right? So there's a lot of units there. How are you going to figure that out? We can use equalities to help us figure out that dosage. The last thing I want to talk about real quick in chapter 1 is this concept of the scientific method. There's a really good video on the difference between a theory and a law in the resources page. It's just kind of one of those pet peeves of mine that people have. But again, we will be utilizing this as we kind of go through logic of how we come to conclusions in chemistry, right? There's some sort of observation in nature. From that, we go, I wonder what that is. Maybe it's this. And then we test it and it's either wrong and we got to go through and do it again, or it's right and we develop a theory off of it. Again, right, this video is posted into your suggested videos to watch. So I would encourage you to do so. Okay, that is the end of chapter 1. We're going to move on to chapter 2 unless there are any questions. All right, moving on. Again, like I said earlier, your homework will be great practice for this. you got to read the textbook, you got to read the textbook, you got to read the textbook. And then next class, or, you know, because we're going to not have, we're doing no Zoom next on Thursday, start emailing me questions and I will start responding to them right away. So we're going to start talking about atoms and molecules, right? We talked about this idea that an atom is the smallest identifiable like unit of an element, and that molecules will be, you know, many atoms together. So again, here for chapter 2, your suggested readings, do your homework. We will be talking in depth at these topics, but sections 1 through 7 are all fair game. So when we look at a periodic table, we have these symbols, right? Sometimes it's a whole word, sometimes it's just a symbol. And so for an element, basically we will have either a 1 or 2 letter symbols to represent that element. Proper kind of grammar for this is, if it's a one letter element, it will always be a capitalized. If it's a 2-letter element, for example, something like calcium, aluminum, magnesium, something like that, the first letter is capitalized, the second letter is not. This will kind of just happen based off of how much homework and practice you're going to have to do, but you will need to memorize and, you know, kind of be comfortable knowing the symbols for the elements 1 through 20, as well as these extra ones here. Trust me, it'll just kind of happen from all the homework and practice you need to do. But in a online situation, it's a little less necessary because you will have access to your notes. We will talk a little bit more about this on next Tuesday in terms of what's acceptable for notes. At the end of this unit, there is kind of a, you know, what to expect when we have Zooming assessments, and it kind of talks about, you know, notes and everything like that. But we'll go through that in a little more detail. Obviously, the human body is made up of a bunch of different elements of different things that you might not necessarily always think of. Obviously, oxygen, carbon, nitrogen, hydrogen, these are the big ones that make up the bulk of our body. But we also have things like calcium in our bones and teeth, sulfur, which is super important in everything from neurotransmitters to proteins. We have, you know, our bodies are have a lot of electrochemistry in them. So we have things like salts and metals in them as well. Iron in our blood, in our hemoglobin. So a lot of really important different elements in there. So you may have seen chemical formulas before that look kind of like this: COCO2, or in the case of H2O. You may have always wondered, why is this a little 2? Why can't I make it a big 2? Again, this is one of those things where it's really, really important in chemistry, whether it's a subscript or, you know, just kind of in line with everything else. And this comes down to telling us how many of each thing are in there. So for example, in the example I have here of carbon monoxide, CO, this molecule is telling me, this formula is telling me I have 1 carbon atom and 1 oxygen atom, and that makes up this molecule. CO2 tells me that I have 1 carbon atom and 2 oxygen atoms. When we have a little subscript number here, whatever element is before that subscript, that's how many of those we have. Now, if I had a 2 in front of this whole thing, if I had a big 2, CO2, that would mean I have 2 of these whole molecules. Okay, and if I wanted to have something that was 2 carbons and 2 oxygens in a molecule, that would be C2O2. For example, H2O2 is peroxide versus H2O. When we are writing chemical formulas, there's a couple like rules we have to how we write them out. If there is a metal in the elements, we're going to write that first. So for example, sodium chloride, table salt, is NaCl. Sodium is a metal, chlorine is not. We don't write it as ClNa. Now, again, what's really good here is the more practice you do with this, which you'll get through your homeworks and everything like that, the more this will just become natural. We're going to kind of learn a new language, the language of chemistry here. And what ends up happening is the more practice you do with it, the more you'll inherently start kind of being like, yeah, like that makes sense there. That sounds funny, you know, kind of thing. That doesn't sound right. That does sound right. So you'll get some practice with that. We will typically, when we have two nonmetals, for example, something like nitrogen and oxygen or carbon and oxygen, those more to the left side of the periodic table will be written first, followed by the ones on the right. And we'll talk a little bit more about why that is later. We also have things called polyatomic ions, and we'll talk about these in a little more detail in our next chapter. But when we're writing these out, we could have a chemical formula that looks something like this. You may have even seen something like this before, but we're going to start breaking down what this is. Right now, we're just trying to understand how a formula is written. We'll go through why there's parentheses and all that kind of stuff later. If I see MgNO3 what this is telling me is, okay, Mg, this is magnesium, this is my metal. So there's a metal and a non-metal in this, which means my metal is going to come first. And then I have this NO3 thing, and it's got parentheses around it with a 2. Just like in math, if this was a math problem and you saw parentheses and then a 2, this would mean that I have 2 of these. Does that make sense? That I have 2 NO3s, right? So the NO3 in and of itself, just like we had CO2, NO3 means I have 1 nitrogen and there are 3 oxygens around it. And I have 2 of those for every one of my magnesiums. That's what that's telling me. So Mg, NO3, 2. We will find out later that NO3 is what we call a polyatomic ion. We already learned in chapter 1, polyatomic means a many-atomed molecule. So this NO3 is a little molecule all into itself. Yes. Whoop.
So I guess what would be there to prevent putting the 2 in front of the nitric oxide after the magnesium?
If I put the 2 right here?
Yeah.
If you put the 2 right here, you've no longer have the Mg bound to the NO.
Okay.
So you need to do it in a way where when you have a number that's a big number in front of something, you have 2 separate things then. So good question. Any other questions with that? Okay. So we will have different kinds of formulas. And I know this is kind of a little crazy. We have something called an empirical formula, and this is just something that gives us ratios. This will become more important when we start getting into our biochem and organic chem sections, where we will see kind of classifications of molecules where we go, okay, the empirical formula, these are all molecules where the carbon-hydrogen ratio is a 2-to-1 ratio or a 2-to-5 ratio or something like that. And then there's different ones that exist within that series. A molecular formula, if you've ever seen a chemical compound before, a chemical formula, you've most likely seen a molecular formula. And this is the actual number of atoms in there. So for example, in hydrogen peroxide, the actual molecular formula is H2O2. That's the molecular formula. There's 2 hydrogens and 2 oxygens in an individual molecule of hydrogen peroxide. However, the empirical formula, the ratio is HO. It's a 1-to-1 ratio of oxygens to hydrogen. Depending on what you're doing, you would need to know that information. If you are someone doing analytical chemistry and you're trying to determine an unknown compound. Perhaps you are doing a toxicology report and you need to find out, what this unknown metabolite is in a patient. The first thing you're going to get is probably mass spec done on whatever sample you have. And that's not going to give you a molecular formula. It's going to tell you there's this percentage of hydrogen, this percentage of oxygen, this percentage of carbon in the sample. So you're going to be able to figure out the empirical formula pretty easily. And then from there, depending on, what's happening with the patient, other symptoms they're seeing, you're going to go, oh, I'm in this class of a 2-to-2 to 1 ratio of this compound. That's this class of poisons or whatever. And then you can kind of start backtracking it from there. So unlike you may have seen on TV, we don't always have a machine that you can just like throw something in and be like, yes, it's this. It's typically a lot harder than that. So that's why we would need to know empirical formulas. When we talk about the atom, you may have already seen kind of a picture of something like this. For the purposes of our class, we're going to go with this kind of setup of an atom. In actuality, this is not actually what we believe an atom looks like now. We are on what we call the quantum theory of atomics, of atomic molecules. And it's a little different, but we are not going to have the time or the ability to go into quantum mechanics in this class. So phew, you dodged the bullet on that one. I will briefly talk about it here and there, but for the most part, this is a perfectly serviceable model. This is called the Bohr model, after Niels Bohr, who discovered it, and it does a really good job of explaining things, but in a technical, how we believe currently the world works, it's inaccurate. And it really just has to do with where the electrons are. We do believe that in the center of an atom is the nucleus. And in the nucleus, this is where the protons and neutrons are. These are what we call subatomic particles, or smaller than the actual atom. At the beginning of lecture, I talked about the concept that the atom is the last time that we can identify something as carbon, nitrogen, oxygen. I cannot, if I look at an individual proton, or if I look at an individual electron, I can't say, that's the electron from an oxygen, or that's the nitrogen neutron. I can't do that. They are indistinguishable from each other. So an atom, and what makes an element unique, is really the combination of these subatomic particles in a certain ratio. It's the recipe of these three things together, neutrons, protons, and electrons, that determines an element. That's what does it. That's what an element is. There's no magic to it. It's literally these combinations, these recipes for an element. And that's why an atom is the last time we can distinguish a specific element. Now, we will find out really the nuts and bolts of what makes an element is going to be these guys right here. Electrons will come and go, and we'll start talking about that in a little bit. But inside the atom, those subatomic particles, protons, neutrons, and electrons, the nucleus is going to be made up of the protons and the neutrons. And we could kind of think of that, if we're looking at the Bohr model, we call it the planetary model. The nucleus would be the sun. And then the electrons are like the planets rotating around it. Like I said, not accurate in terms of what we currently understand how the atom looks, but it's good enough for what we're going to be doing with it. Within the nucleus, there are protons, positive. Protons are positively charged molecules, or excuse me, particles. Neutrons are neutral. They have no charge to them. Electrons have negative charges, okay? So with the exception of electrons, there's a lot of alliteration that goes on there that kind of helps with the memorizing of things. But it wouldn't be surprising. The atom is kind of being held all together, right? The protons are sitting in the center, and the neutrons are hanging out there too. So what the heck is keeping all those electrons floating around that neutron, or excuse me, that nucleus? It's electrostatic attraction. We have a positive charge in the center, negative charge floating around, and its attraction is just like magnets. And there's a reason those electrons don't want to be too close to each other either, right? If I have two magnets that are same charge, what happens? They repel, right? So electrons want to be far away from each other, as far away as they can be, while still being a part of the same atom. We'll learn later that the way chemistry happens is all about electrons. Electrons do all the chemistry. So sometimes electrons are given, some are taken, some are shared. The ones that are on the outside, the Plutos, I'm going to say Pluto's still a planet here, whatever. The Plutos, the Neptunes, right? The guys on the outside, those are the ones that are going to go do all the chemistry, okay? And sometimes they get close to each other and they actually repel. And that repulsion that we're going to learn about later is actually how we can predict the shape of a molecule, because we know how many electrons there are and what configuration they're going to have to be as far away from humanly or subatomically as particles away from each other as possible. And that will dictate how a molecule will look and how it will branch out. It's pretty cool. All right. So in terms of what we have, a proton, a neutron, electron, when we're talking about an atom and the mass of an atom, the bulk of it is going to come from protons and neutrons, okay? Yes, electrons have mass. They are matter, but it's so tiny that we don't really count it as part of the atom. And that's partially because when we're talking about, go back to our significant figures, when we measure things, to measure the mass of an atom, we can do that with some pretty precise, powerful instrumentation. But to measure the mass of an electron is very, very hard and not readily available. So when we do math, look where these are and look where these are. Hey, remember our significant figures with rounding? These guys are going to go away. So that's why we don't contribute, they don't contribute mass to the atom. They really do. But in terms of how we go and measure them in our day-to-day lives, we pretend they don't have mass to them, but they do. So when you're looking at like the mass of a sodium atom per se, what we're really doing is adding up the mass of the protons and the neutrons. The electrons are just kind of hanging out and doing their thing. All right, so here is some important nomenclature or some important definitions that you're going to have to know. There's something called an atomic number and something called a mass number. And students love to confuse these. So this would definitely be some flashcard things to work on. An atomic number is equal to the number of protons and neutrons, or excuse me, sorry, I'm getting ahead of myself. Atomic number is going to be the number of protons and electrons. So if I have an atom on its own just hanging out is neutral. It has no overall charge. But we just said protons and electrons are charged, right? One's positive, one's negative. How could I have something that is overall neutral? I have the same number of positive charges as I have negative charges. When they cancel each other out. So in a neutral atom, the atomic number, so if you look at a periodic table, hydrogen's 1, helium's 2, right? We go so on and so forth. In this case, sodium is number 11. That atomic number represents the number of protons and electrons in the neutral atom. We're going to find out the periodic table, for just being like this one thing, tells us so much information. It is such a powerful tool. It's so cool. It's like the cheat sheet of cheat sheets if you know how to use it. Without anything written on it, you can figure out a shit ton of stuff if you know how to read it. So the first thing you need to know how to read is the atomic number. And that tells us how many protons and how many electrons are in a neutral atom of that element. The next thing is the mass number. And that's typically when you look at the periodic table, it's this little number down here. Okay, and we'll talk about it because there's a little bit of difference between a mass number and an atomic weight, and we're going to get there in a minute. But the mass number is going to be number of protons and number of neutrons. Okay, that's the mass of that atom, right? And that makes sense because we already said that we're not going to contribute electrons to this, right? So the mass of the atom is going to be the number of protons plus the number of neutrons. The atomic number is going to be just the number that represents how many protons and how many electrons there are in the neutral atom. Okay, atomic number. Atomic number is going to be unique for every single element. That's why when you look at the periodic table, that number for each element is there. It is the same. All sodiums are atomic number 11. Okay, all sodiums, regardless of what's going on. If it's sodium, it has 11 protons. Please note that I did not say 11 neutrons and I did not say 11 electrons. The thing that defines something as an element is going to be the number of protons. I'll say that again. The thing that defines an element is going to be how many protons it has. Neutrons and electrons can change, and it can still be sodium. We're going to talk about how that happens in a little bit, but the thing that defines an element is going to be the number of protons, and that's why the atomic number for an element will always remain the same. Okay, so then we have mass number, right? That's the thing where we say, okay, if I have, you know, for example, you know, lithium, and my mass, I'm going to have 3 protons and 1 neutron or whatever, right? Whatever it's going to be. That added up is going to be how much the mass is of that individual atom. Now, in a neutral atom, like we said, the number of protons and electrons will cancel each other out, right? And that's how we get no charge overall. Okay, so mass number. It represents the number of all particles in the nucleus. Remember, for nucleus, where the protons and the neutrons are, that's going to represent, like, you know, the overall mass of that specific atom. Now, this is where things get weird. If you have a periodic table out, look at it. If not, go look at a periodic table after class in like 7 minutes. Mass number has to be a whole number, right? We're talking about subatomic particles, which we said are like the smallest, as we know of right now, unit. So I can't have half a proton, right? So my mass number is going to be like 5 protons and 2 neutrons or whatever. 7, a mass number of 7. I can't have 7.2. Now you might be going, well, wait a minute, Dr. Sardo, like when I look at a periodic table, that number underneath the symbol is like 35.7548245, right? Like some crazy decimal place number. And you're like, well, where the hell is that coming from? We're going to talk about that. That comes from the isotopes, and that's going to be our next concept. So we talked mass number, or we talked atomic number, we talked atomic mass. Now we're going to talk atomic weight. Atomic weight is going to is the number that you see underneath the symbol in a periodic table, the general number that we see. There are, not every element has them, but a lot of them do. The concept of an isotope. Remember how we said the proton is the thing that defines an atom or an element? And we said that neutrons and electrons can change. If I have something like chlorine, all chlorines will have 17 protons, regardless of a chlorine I find in the ocean, a chlorine I find out in space, a chlorine I find deep buried in a mountain. They will all have 17 protons. That defines it as chlorine. Some chlorines, though, will have 18 neutrons, and some chlorines will have 20. And what happens is they're both chlorine, but they're different isotopes of chlorine. The place you may have heard of different isotopes would be if you've ever heard of carbon dating. Carbon dating is a way that we kind of use radioactive decay to determine how old something is. And I'm talking like way old, like dinosaur bones and like, you know, the Shroud of Turin and shit like that. So carbon-13 is the one that we use in carbon dating. And that is a specific isotope of carbon that we know the radioactive decay of, and we can use how much is left to figure out when something died. So for example, in a piece of paper comes from a tree, right? And so if we have some sacred document that, you know, we want to go, oh, is this fake? You know, it's supposed to be around 2,000 years ago that somebody wrote it. Well, if we carbon date it and it comes out that it was made in the 1600s, we know it was a medieval forgery instead of an authentic document, because we know when the tree was killed. So granted, you might have 100 years, maybe one way or the other, but we can go with that. Same thing if you're looking at, you know, artifacts from like the Ice Age, bone fragments, things like that. We can't carbon date a piece of metal. We can't carbon date, you know, a shell, or well, we could carbon date a shell. No, not really. Because if there's remnants of the mollusk in it, we could, but it needs to be something living. So anyways, this idea of isotopes is how we end up with this number with decimals, right? Because we said that we can't have a decimal because it's protons and neutrons, and that makes up the mass. We have an atomic weight. So in the universe, we have these ratios as we understand them currently, right? Chemistry and science in general is all about how we currently understand something. And it's going to be a weighted average of that, just like your grades are done. So if you can understand how to calculate an atomic weight, you can also calculate your own grade. And so when we have an isotope or an element with isotopes, the atomic weight we get out will be an average of those. And so here's a really good example of that for magnesium. So there are 3 different isotopes of magnesium, magnesium 24, 25, and 26. And the bulk of the magnesium in the world and universe comes from magnesium 24, but we do have amounts of the other ones. So when we go ahead and mass this all out, when we get the you know, the weighted average of magnesium, we end up with 24.31. So the bulk of it came from the 24, but a little bit comes from these guys. And that's how we end up with the decimal place. Your homework will give you a lot of practice with the atomic weights and isotopes and that kind of thing. And this is how we end up with that 24.3 that we see on the periodic table. All right. Again, I'm going to skip ahead just to get to the concept of the mole with the last few minutes that we have. I strongly encourage you to go ahead and follow through with these notes. Go look at the resources. The resources for chapter 1 are so robust because it's just something we have to bang through to keep going. So please go look at them and then start asking questions. Start asking me questions. Email me. Literally my job, I get paid to answer your questions. You're not bothering me, okay? Please, especially online and especially in this class, I want you to succeed, but the only way that's going to happen is on you. Like, this is on you guys to drive the bus here. And if that's not for you, I'll see you in the fall in person in 16 weeks. Anyway, so the concept of a mole, it's going to be a counting number, just like we use the term dozen. If I say I have a dozen eggs, you know that we have 12 eggs. If I tell you I have a ream of paper, I have 100 sheets or 500 sheets of paper, right? It's a counting number. And so a mole is a counting number that's a really big number. It's 6.02 times 10 to the 23. It's really, really big. I have a really good video posted of how big this number really is. I encourage you to go look at it. Here's it written in standard notation. And this is why we use scientific notation, because how many times are you going to screw writing that in your calculator up? So that's why we type it like this. And it is a really good way to count in chemistry, because chemistry is full of really, really big numbers and really, really small numbers. And it will be a way that we will count how many particles, how many atoms, how many molecules of something we have in a sample. So it's going to be a really important conversion factor. So you will have the rest of the day to go through these notes, do these practice problems that you have. Class is over, so I'm going to have to end it here. Chapter 3, you're going to have to go start looking at on your own. Go read it, start asking me questions. Thursday is chapters 4 and 5. They're pre-recorded lectures, so you can pause them and go through those at your own leisure. Those are graded though, so make sure that you go through that. I'm going to stop this for 1 sec. I'm going to go back to our Canvas page just for a hot minute to remind you of where everything is, and then I will answer questions in just a second. So again, make sure you go through the Getting Started module. I kind of did a dick move, but it's just to force everyone to go through it. You have to complete all of the items in here to be able to access week 2. Okay. I did that because you're going to get so lost if you're not going through this stuff first. It's a dick move. I know, I'm sorry, but you have time. So once you do that, you already have access to week 1. So that shouldn't be a problem. Week 1, here are our lecture slide. Here are those non-graded, really helpful videos. Here's your lab stuff. Here is day 2. Here are the lecture slides for day 2. Here are helpful videos for day 2. They are the not graded ones. Here is your quiz. You need to set up your homework and OWL and everything before you can take the quiz. Then you'll have the pre-recorded lecture video. This one is graded. When you click on it, you can watch it right here. I'll see, and since it's embedded in Canvas, I'll be able to see you do it. Doesn't matter how many times you watch it or if you pause it or any of that kind of stuff. Just go watch it by the due date. Sorry. Chapter 4, chapter 5, those are the slides. They look just like the slides that you saw today. They're PDFs, print them out, do whatever you want to do with them. Right, all the reading, all that kind of good stuff right there for chapters 4 and 5, the pre-recorded videos for 4 and 5. And then you will have your quiz, pre-recorded videos. This video, really, really helpful. It's from my Chem 200 lab. But it's me with a tablet just drawing a ton of molecules. So it's really great practice. I go through all the math on how to do it. it's basically like if I was on a whiteboard kind of thing. So go ahead and look at that. My Surface broke, so I'm on a laptop now, but hopefully my new one's coming, which means I'll be able to start drawing again. We'll definitely have it by the time we get to organic chemistry, when it'll be useful. Here are your homework assignments. Please look at this. This is the only thing that's like a check off on doing it. This is taking assessments via Zoom. Look at this before next Tuesday, because our quiz next Tuesday, quiz 3, is going to be via Zoom in class, just to kind of make sure we all know what we're doing before the exam. Here are your homework assignments. Here are those worksheets, right? So this is basically a ton of blank worksheets, all the keys for the worksheets. I have extra slides. Here's that guided practice, redox. I have a whole extra PowerPoint presentation on that. Everyone's grinning like, oh my God, look at all this stuff. This is what happens in an accelerated class in 8 weeks. And then lastly are those videos, the videos for each section. Please go look at those as well. And that will basically take us through the whole week. Even though I'm not going to be synchronous time on Thursday, I will have access to email, all that kind of stuff. So shoot me emails, shoot me prontos through Canvas. I'll get to them. I think they figured out the issue with the email coming from outside sources. If you email me through Canvas, I definitely will get your emails. There was a problem with the SDCCD emails with outside stuff and sending them. So if you send me emails through Canvas, I will get them. You can send me messages through Pronto as well. And then day 3, we'll start off with a quiz, and then we're into chapters 6 and 7, and then chapter 9. And then that's the end of our first unit. And then we will take exam 1 on the first day of week 3. I know everyone's eyes just went, ooh, that was right, 9 chapters. So again, I'm not trying to be a dick. This might not be for you. If you have work, if you are taking other classes, it's going to be a lot. If this is all you're doing for the next 8 weeks and you're going to live, breathe, and sleep it, you can do it and you can bang this out. But it's going to be a lot and it's going to be on you. Okay, that's it. If you got to go, run, go. And I will be around to answer some questions. If you want to talk to me privately, just send me a chat, and then we'll meet up privately. Otherwise, raise your hand and I'll start banging out questions. All right, Yasmin.
So this lecture will be up on Canvas, right?
What do you mean this lecture?
Because it says that it was recording. So
yes, I obviously I can't post it till we're done. But yeah, right. It'll go into the videos section.
Cool. Okay, awesome. And then in terms of, I mean, I know I already can tell it's going to be many, many hours, but do you have like a rough estimate in the past of how many hours students spent per week for the material?
Yeah, so in a 16-week semester, it's an average of 30 hours.
Okay.
For the week. So in a 8-week summer session, it's hard because we've never had it where we only have 2 days to do it. Typically, if this was in person, you would be meeting Monday through Friday or Monday through Thursday for 2 hours every day. And that's not happening. So right. This online, it's a whole new, at least 30 hours a week is going to be the minimum for this.
Okay. Thanks.
Each homework assignment on average takes at least an hour and a half.
Okay. Cool. Thank you.
Danielle.
Okay, this is like not a personal question, but it has to do with me. I'm taking one other class. It is a Black Studies class, and it is completely online, like no meeting. Sure. And I was just looking at the class, and it just seemed like we have just like one quick check-in assignment and an exam at the end of like a couple weeks. So it seems pretty chill. But then I'm also working throughout the week, and on Saturdays and Sundays I am a student nursing assistant, so I'm also working 8 hours each of those days. Do you recommend dropping my Black Studies class?
Oh man, I hate when people like, you best. That's the best way I can put this. And I made the effort. The first 5 weeks of our 8-week class, I've put all the homework assignments up. I've written the tests. Like, it's all there to look at in terms of what the workload is going to be. The best thing I can say for you is to go look at the calendar, go look at how many assignments there are, go look at Cengage. You have until, I think it's the end of the week or the 26th or something like that to drop with like out the W and all that kind of stuff. And the Cengage is free for the first 7 days. So like there is like a no holds, like go give it a shot kind of thing. See if this is going to happen for you or not. And if it isn't, I will see you in September. Like, you know what I mean? Like, I get it. It sucks that you won't be able to do it over the summer if that's not the case for you, but you're still going to be able to take the GOB, which is a 1 semester instead of 3 semester situation. Otherwise, it's really each individual student, what your ability is in terms of how well you study. You know, you as a student in terms of your reading comprehension and your ability to kind of just drive home and drive the bus right now kind of thing. So it's really going to be on you. But I would say any class is going to be taking away from being able to work on this and work too. I know it's a shitty situation. I'm not going to lie. Like it's hard. So that's the best answer I can give, which is a complete not answer. And I'm sorry.
Well, that's great. Thank you.
Okay. Other questions? I know a couple of you have texted me already, chatted me, and I will set up private Zoom breakouts when necessary. Any other general questions, concerns? Okay. If not, when you're ready to peace out, go away. Good luck, Godspeed, and start emailing me questions. All right. For those of you who are chatting me, I will do the breakout room as quick as humanly possible. So just give me a sec to answer you all.